In our previous episode, we talked about circular motion. We learned that the moon is a projectile circling the Earth under the action of gravity. We learned that Newton's universal law of gravitation applies to objects on the surface of the Earth as well as to the stars and planets in the heavens. We mentioned that the moon moves in an almost circular path with central acceleration. The gravitational force of interaction between the Earth and the moon is of the same nature as the weight. We have so far learned Newton's laws of motion, inertia, acceleration, interaction, and momentum, as well as gravitation. Today, let's explore how these ideas are used by modern scientists in sending men to the moon and in launching artificial satellites that revolve around the Earth. Join us in this journey into space as we study spaceflight here on Physics in Everyday Life. Like the cannonball, rockets and aircrafts are also projectiles. Rockets were invented by the Chinese over 750 years ago. Back then, they were just fireworks which use a kind of gunpowder as fuel. Rockets such as these are called solid fuel rockets. These days, however, modern rockets are liquid fuel. To understand how rockets work, observe what happens to this inflated balloon once it is released. Here's our balloon, and we're going to release it. The balloon moves around the room as it deflates. And why is this so? The balloon moves because of Newton's third law of motion, which states that for every action, there is an equal and opposite reaction. The balloon pushes the air inside out of the opening. This is called the action force. The air, on the other hand, pushes the balloon in the opposite direction. This is the reaction. Rockets work on the same principle. When the fuel is burnt, gases are pushed out of the rocket. At the same time, these gases exert an equal and opposite force to the rocket, causing it to accelerate. Because rockets have to move into space, a great amount of fuel has to be carried. A rocket is made out of several rockets linked together. The rockets are fired in stages. As the fuel is used up, the lower stage is released to relieve the upper stage of the extra mass. Each stage lifts the craft until finally the payload is put into orbit or achieves a speed that is fast enough for it to leave the Earth's atmosphere and join into space. Putting a payload into orbit requires control over the speed and the direction of the rocket that carries it above the atmosphere. A rocket is fired vertically. It is instantaneously tipped off from the vertical course. Once above the drag of the atmosphere, it is aimed horizontally, where it is given a final thrust of 8 kilometers per second. If the horizontal speed is greater than 8 kilometers per second, it will overshoot a circular path and trace an oval-like path. This is what we call an ellipse. As it moves away from the planet, upon takeoff, it decreases its speed. It slows down to a point where it no longer recedes and then begins to move back toward the planet. The speed it loses in receding is regained as it moves back. In the end, the satellite crosses its original path with the same speed it initially had. An ellipse is traced, and it is now an artificial satellite. More on spaceflight when we return. Welcome back to Physics in Everyday Life, dear teachers. Let us continue with our far-out journey into space. A satellite remains in orbit because of gravity, not because it has escaped from gravity. As we have learned, no matter how great the distance is, the Earth's gravitational force still acts on it. Although, as we have learned, the gravitational force decreases with increasing distance, it approaches but never reaches zero. Because it is in orbit, the satellite falls or deviates from the straight line path it would have followed if there were no forces acting on it. But it doesn't crash down to the Earth because it has sufficient horizontal velocity. As it falls, the surface of the Earth curves away from it, causing the satellite to fall around our planet. What happens to the astronaut and everything else inside the falling satellite or spacecraft? Since the astronaut is inside the spacecraft, there is a force tending to accelerate the astronaut down to the floor of the spacecraft. At the same time, there is a force on the spacecraft that accelerates it downwards, so the floor tends to fall away from the astronaut. In other words, everything inside the spacecraft is in a free fall. Everything inside the orbiting spacecraft falls at the same rate as its surroundings, so it appears to be weightless. If you stand on a bathroom scale in a moving elevator, you would find variations in your weight. Let us look at our figure here. For the first case, we have an elevator which is at rest, and therefore the scale reads normal weight. If the elevator accelerates upward, as shown in this second case here, the bathroom scale and the floor of the elevator push harder against your feet, and the spring inside the bathroom scale would be more compressed, and your reading would increase. And so we have here scale reads greater than normal weight. If the elevator accelerates downward, the support force of the floor of the elevator is now less, and the spring inside the scale would be less compressed, hence your weight reading would decrease. And so we have here apparent weight less than normal weight. And finally, if the elevator cable breaks and the elevator falls freely, the reading on the scale would register 0. According to the reading, you would be weightless. But of course, you are not weightless. Under this condition, although there is gravity, it does not manifest as weight because there is no support force. Everything is falling just like inside a spacecraft in outer space. You don't feel the usual effects of weight because the support force is absent. Rather, you are in a state of apparent weightlessness. The condition of weightlessness, therefore, is not the absence of gravity, but the absence of a support force. There are physiological effects associated with weightlessness. Perhaps the most visible change is that the astronaut's face becomes puffy. On Earth, gravity pulls the fluid in the body towards the feet. In orbit, the equilibrium distribution of fluid shifts towards the upper body.